So this is part 3 of review lecture 23 of differential equation and exponential of a. So we have discussed the stability in the previous one. So let's discuss about the third one, which is introducing these e to the at and e to the lambda t as a solution of u to the t. This term right here might be similar, but they are different. One is the power of a matrix a to the t, and one is the power of the lambda, the capital lambda of t. So let's see how we can derive, how we can get this formula, how we can derive from here to here, which is, I think, also one of the important thing in this lecture. So we start from here as always. But we're interested in, can we expand U in terms of the eigenvector? So we have this U is the S is the eigenvectors matrix. So it's just like all the eigenvector together in the column. So this is S, okay, and times some constant or some coefficient that combines all of them so that they equal to U. And again here you will see that I will interchangeably set U instead of U of t, or the same goes for V. Now V is not a constant here. Instead the S is the constant. The S is just, it might be counterintuitive because I just said the V is the coefficient to this, but see that S is just a number, right? It doesn't have any component of t. But we interested in expressing this U of t into something else. So imagine that S is just a bunch of number here, but you don't have any element of something inside t. So that's why you need the Vt. So let me just write the V as this one, the one with the little slight dash in the beginning, just to distinguish better between this and U. So that's the idea. Okay, so that's the first important idea. So the ut is a combination of the eigenvector as a basis times the vt that we define here. Okay, so let's plug u into here. Again, you see I don't write the t here, but I just said I can plug it here. So that's also explains why I said the ut equals to u. Okay, so let's do that. So again, s is constant, so I'll just let that out as, okay, and then I have the v time over the t, and this will be equal a to the u is the s v. Okay, again, I'm just ignoring the t, but remember the v and the u is the function of t. Okay, so let me continue this. I want to put the s here, so I'll multiply this by the s inverse, so it goes into the right hand side. See, because here, and this becomes the identity, and so on. You can see. Okay, so we have this. Okay, and then here, if you remember from our previous lecture that about the diagonalizing, if I can say it properly, diagonalizing a. So the a and our eigenvector matrix S is the S of those lambda. Right. So we move it to the left hand side, so we have this. So this is just a lambda here, a big capital lambda. So a matrix with the lambda or eigenvalues in the diagonal elements, and we have phi here, v, and this is dv per divided by dt. Okay, cool. So remember in the beginning I introduced you to the solution of du over dt is the lambda u, and the solution to this is this one, right? So can you see that this and this are really similar? So this one actually just we have right now like v is a vector here. Okay, let me make it bold. So I want to put that, emphasize that v right now is a vector. So what we have right now is like the v1, the first order of 1, and the second v is our lambda and v1. Same goes lambda 2 v2. Okay, so this is actually the same thing as this. You see this and this are the same, but this is just expressing it in terms of the vector, okay, instead of just like one scalar value or one variable here. So these are multiple variable here. Okay, so I hope you can imagine that. And that also means I can express this v, I can find a solution of v, right, by following this format right here. So let me write that down here. So I have v, which is something, some constant, anything, and the exponent to the power of lambda t, right? Okay, but now we are talking about vector. Okay, so let me bold that down, vector. So this is actually a new introduction of the term. Instead of writing that small lambda, I'm writing the big lambda here of t. Okay, I will delete these. So I hope you see that. So let me write that down right now in all blue colors. Okay, so what comes next, actually I have not told you before. So the constant here, see, because we don't have the x eigenvector like we have it here in the ut, we don't have that. So what we can do here, actually remember that v, let's talk about the single case, okay, because that is pretty simple. Okay, let's do it in another column here. V of t is something constant equal to this lambda and t. Actually we can get this constant value, we can get the solution to this, and what it is, by setting this to 1, right? So when does this equal to 1? Exactly when t is 0. So anything to the power of 0 is 1. So c is actually the phi at t equals 0. And remember, we don't have that eigenvector here, we don't have that here, so we can do this. Okay, so that's why we can express this vt is actually v0 e to the power of lambda t, right? And if you say, okay, how about if we express vt as e to the lambda t? That is also correct. This will also lead you to this derivation. See, if dv dt, that will be lambda, so dv dt, it will be also like lambda e to the lambda t, and this will be lambda v. But here I'm assuming the constant is 1, and here I'm putting it in more general term. So why is it? Because I want to use this v0 next. You will see this coming. Okay, so let's continue with this one. So this is only for one function. This is not a vector. So how to transform it in a vector? I will bring up here. So I will bold this one again. So this is a vector, remember? So this is just same as saying that this is a collection of those vector at time 0, right? And then C is actually here right now, and then we just express the rest of them. Yep. So this will be useful here because we want to substitute this into this. Okay. Okay. So there's quite a small mistake. So it's not that I want to substitute this into this, but this is where from this I can get this. So this is just like putting this in this term that we're familiar in the first part, and we get this. We can express that the vector of v in terms of v0 and e to the power of capital lambda t. Okay. So we are now interested in our initial formula, which is, in this case, it's not this one. Now remember that we can express the ut as it is in the first part, or we have another expression here, which is the eigenvector times the vt. So we will use this and we will continue with this. Let me remove this one. Okay. So let's write this one again here. So ut is the s of our vector v, collection of all the v t. Okay. So this is also naturally this is also collection of v, right? So we plug this into here. So we have the v0, or let me put it in another way. E to the power of big lambda t v0. Okay. Now why I can switch that? Remember that E is just a diagonal matrix with all the component of E in the diagonal like this. So it's really valid to switch it up. It's just in the end just a constant. Okay. So let's move on. And now I am interested in the expressing the v0 in terms of u0. Now how can I do that? Is by modifying or playing around a little bit with this formula. Okay, so if we have the ut equal to the s times vt, then we can also plug the t equal to 0. So let me bring that down here, and let's write it down. So u of 0 is the s, the eigenvectors in the column, times the v0. And we can say the v0 is the s inverse of u0, right? And keep in mind that what we're doing here actually by setting t to the 0 is that if vt is a solution of e to the lambda t, then we're just switching off all the e. So we left off with all some kind of constant element here without any e. So that really gives us the benefit of an easiness in terms of calculating it further. So let me explain it later on when I get into those. So actually this v0 is equal to this, and I can plug that in here. Let me write that down. ut to the s e to the capital lambda t, and I have the s inverse of u0, right? So what I mean by what I just said, it seems like this is a constant without the e term. So if you see here, what we have is this one is a matrix of all the eigenvector here, okay, in the column, and this is just a bunch of, again, that this term, the exponential to the lambda t in the diagonal. So this is lambda 1, lambda 2, and so on, with this is 0, 0. And this one here, there's actually just like a constant here. You see? So why is that? Why is that? Again, because this phi0, remember the phi0 is the constant again. We're just switching off all that t. So t equals 0, switch off. So we are left with the constant. It seems really enlightening when you get into this point. And you can see that we have what we have here. If I may just delete this one quickly. What we have here is really similar to what we learned in the previous session, where we have the diagonalizing of A. So let me write that down quickly here. So A of all the matrix of eigenvectors is the x times the lambda. Then A is the x lambda x inverse. You see the similarity here. So this is just expressing it in terms of the exponential. So accordingly, we can say, okay, so this is our e to the A matrix AT times U0. And remember, this is still our UT. Okay, and we're just expressing it in a different terms, you know. So this is what we have in this part, and this is what we have in the initial part. But actually, this is still brings us to the same equation, this one. C1 to the x and the x, okay, and so on. Why is it? Because remember, yeah, what I told you before, so this is just a matrix of eigenvector, this is just that e part in the diagonal, and this is a constant, so in the end we still have this, and this is still ut. But we just have an access to expressing something in terms of e to the at u0. And I think this derivation is the most important part in this part. And next I will describe how to easily express, or an alternative way to express this in terms of the infinite series. So till then, bye bye.